This is topic 3.13, the Beer Lambert Law. Our outcome is I can explain the amount of light absorbed by a solution of molecules or ions in relationship to the concentration, path length, and molar absorptivity. So you're going to open up this Beer's Law PhET simulation, and you're going to complete the Beer's Law AP Chemistry activity. This is a Google form, so you're going to enter your responses as you work through the simulation. After that, you have an example of an FRQ here, and you're going to complete this on your own and then check your work by watching the AP Daily video for topic 3.13 in AP Classroom. So the solution to this problem is available through that video. So looking at our simulation here, we're going to start by turning it to absorbance. And we can turn this on, and this tool basically compares the light before to the light after, and we see that we have an absorbance of 0.51. So that means about half of the light has been absorbed by the solution. We can change the wavelength that this is on, so we can change it to different stuff. Notice that this absorbs very strongly whenever we shine green light on it. This is a red mixture. If we change this to a green and we put it on green, we're going to see that we have basically no absorbance. We can measure the size of our path length. So right now it's 1 centimeter. We can make it bigger or smaller. So that's going to change the transmittance there. So if I make this wider, there's more particles to absorb that light. If I make it narrower, there's less particles to absorb the light, so we get a lower absorbance. We can also play with the concentration. So if I increase the concentration, we see that the absorbance increases. That's because there's more particles present in the solution. So you'll experiment with this, go through and answer the questions as you go, and use that to complete this activity. For our reflection questions, what is the relationship between absorbance and concentration? So the higher the concentration of a solution, the higher its absorbance will be at a particular wavelength. So when studying colored solutions, absorbance values greater than 1 are generally avoided by diluting samples. So how might this contribute to error during the experiment? So at very high absorbance values, there's very little light reaching the detector, so much so that we're approaching the limit of what the detector can detect. So this might lead us to measure an inaccurate absorbance, which is going to contribute to error during the experiment. So what I would do is I would dilute it by, say, a factor of 10, and then in my calculations, I would just have to go back and account for that dilution.